Hello, welcome back to Decaf-Math, and welcome if you are new here. Today I thought that we could go over slope fields, and in particular we can draw the slope field for this equation, dy dx equals y. And I think that this is a more basic example of slope fields, but I wanted to start with this so that we can review whatever concepts we need to and just take our time. And then in future videos we can do other examples, and I won't have to go as in depth with the explanation because we can just build off of what we go over here. So we can do other examples with other stuff where dy dx has x and y in it. But today, let's start with the basics. So, slope fields. So what we are expecting is a bunch of little lines here, okay? And it's going to apply for situations where we have first order differential equations, meaning that we have this dy dx, which is sometimes written as y prime, right? And so we only have the first derivative. Okay, so our equation only involves the first derivative. So no second derivatives, no third derivatives, no whatever else. Okay, so in general, slope fields will help us visualize what's going on when we have dy dx equals some function of x and y. And if you've never seen this notation before, this might be kind of scary looking, but all this means is it's a function of x and y, meaning you might just have a bunch of x's and y's together, like, x squared y minus y, or x plus 2y, or just even y, which is what we're doing today, because with just y, you can think of it as having 0x plus y, or something like that. Okay, so as long as we have dy dx on one side, and then we have some sort of function of x and y on the other, then this can be helpful. So sometimes when we have this form, we can solve the equation directly. And to solve, what it means to solve is we get y as a function of x. And of course, if you have other variables like x and t or something else, you can extrapolate, right? We're just going to work with two variables here. So to solve this means that we get directly y as a function of x. And then of course, depending on whether or not you have an initial condition that's given, you might end up with something like that, and then like a plus c, which is our like constant from integration. Okay, so sometimes we can use methods to directly solve the differential equation, and sometimes we can't. So for instance, in this case that we're working through today, we can actually put this y over here, move the dx over there, and then integrate on both sides. So just separating the variables. But sometimes we can't, like if we had a situation where we had dy plus y equals dx minus 5x, for instance, we can't actually integrate on both sides, because we have to take the integral with respect to a variable. So that's not actually going to help. Okay, so drawing out slope field is particularly helpful for when we cannot solve directly. because what it does is, instead of getting this equation, we can kind of sketch out the derivatives at particular points, and then we can kind of follow those derivatives to get a general shape for our function, even when we don't have the exact equation. That's kind of cool, gives us some sort of visualization about what's going on. Okay, but regardless of whether or not we actually can solve it directly, it's still just kind of cool to visualize functions and derivatives in this way. So, before we start drawing out our slope field for this equation, there are two concepts that we really rely on heavily when we do this. And it's kind of a combination of algebra and calculus. So first of all, what we're going to do is take a bunch of these points, okay? And on this xy plane that I already started, right here are axes. And at each of those points, we are going to use our equation to determine what dy dx is at that point. So remember, points on this have x and y coordinates. They're ordered pairs. And then using our equation, we can determine the slope at a point. But it doesn't make sense to just say slope at a point. It's the slope of a line. And that line is going to be the tangent line at that point on our solution, whatever that solution may be. So we are going to draw a bunch of these little line segments, okay? So before we go back to that, let's review what slope means, okay? So the slope of a line is a number that helps us see the steepness. So the general form of a line is y equals mx plus b, where m is the slope and b is the y-intercept. We're not going to worry too much about this b here because we're not trying to find the exact equations of our little slope lines here in our slope field. We're just going to focus on the steepness, okay? So if m equals 0, we have a horizontal line. Our line is just going to look like that, okay? So it's just going to be flat. If m, which is our slope, equals 1, the basic idea is if we move 1 unit to the right, so in x, if our x coordinate goes up by 1, our y will go by 1 also. So it's going to actually be like a 45-degree angle, like that, okay? Assuming that each square here is 1, okay? And you can calculate this by the change in y divided by the change in x, or the rise over run. So that's m equals 1. M equals 2 is going to be a steeper line than this. And so it's going to look something like that, okay? And so m equals 3, you keep increasing, it keeps getting steeper, right? So you can envision like it'll be harder to push the ball up here if this were like the mountain, right? And then if m is negative, so -1, it goes the other way. It's downhill, if you want to think of it like that, downhill. Of course, we're not relying on the rigorous math right now and the calculations, but this is the general idea, right? So m equals -2 means if you move to the right 1 unit for x, then y, the change in y is -2. Okay, so like that. Okay, something like that. And so these are the slopes of these lines. So if we need to review this a little bit more, we definitely can. Usually we kind of draw lines like longer. If we were to graph a line, I would graph it like all the way across. but I'm making them kind of small like this on purpose because when we do the slope fields here, we're just taking little segments. So we're making little teeny line segments at a bunch of different points that have the slope that we're looking for. Okay, so that's one thing. And remember, we can have like, you know, a slope of 1/2 is going to be, you know, not quite as steep as 1, but it's not flat. So it's somewhere like, you know, somewhere in between. Right? Kind of like this, not as steep. So basically we go from 0 being completely flat, we keep increasing, getting steeper, and then once we get completely vertical, there's no slope there. It's like infinite, or it's undefined. And then we keep going around and then we hit negative. So negative, very steep, and then back, and then all the way back down to 0. Okay, and then we're positive again. We can definitely review calculating slope and going into this more another time in our algebra videos. But I hope that that makes sense because that's important here. Okay. Okay. So then the other thing was that the dy dx, the derivative at a point. So we're talking about at a particular point is, so here's like a little definition to know or to review, is the slope of the tangent line at that point. Okay? At that point. Okay. So we are talking about the derivative at a particular point, and that point is going to have x and y coordinates. Okay, so I drew this out without anything else. If you're doing this for homework or you know, for a class or something, sometimes these kinds of problems have these little dots drawn for you, but I wanted to show you that you can do this on your own, you can do this by hand, and that it's not always given. Okay, so I'm just gonna fill some in right now to show you what I mean, but that's not like part of the problem necessarily. Okay, so basically these dots right now, I'm just putting dots at all of the integer, you know, just all these intersections, but these are the integer x and y coordinates. Okay, also I thought that this would be kind of satisfying to watch. But now that I'm actually doing it, it's a little bit tedious, so whoops. But I hope you understand what I mean. So the reason I'm putting the points here is because they kind of lay out a default grid and default points for us to try out some of our x and y coordinates. Okay? And no, we are not going to play a giant game of dots. Sorry. But yeah, so sometimes, like for homework and stuff like that, your teacher will have these dots printed out for you. And that kind of makes things easier sometimes, but that's not really necessary, okay? But basically, these are like the centers of our slope, little slope segments. So for instance, this gives us a way to try out 2, 1. So what we would end up doing is using our equation to tell us the slope of the line at 2, 1. And then we use that number, whatever that may be. This might be like, you know, x times y minus 5y or something like that. It's a random equation, but you plug in your x and y and you get a number. whatever that number is will tell you the slope of the little line that you're going to draw at 2, 1. So, you know, if it's 3, you would expect like a steeper little line. If it's 0, you'd expect it to be horizontal. And you kind of want it to be centered along that point if you can, because it's just a visual representation, so we're just sketching anyways. But you know, you don't want it too far off because you don't want to be bumping into other points. And another thing is you can do this for point. Of course, the more points that you sketch, the more precise you're going to be with like the shape of the function. So you can do like halves if you want to, just adapt to what makes sense for the question. But sometimes this is just already drawn out so that you can just visualize the points, and you can just get straight into testing out points and drawing the lines rather than spending a lot of time, you know, graphing this all. So what we're going to do here for dy dx equals y is we can just set up a table. In this question, you don't really need one, but I thought that we could generalize this process for other equations, so we might as well have a setup here. So my table is going to have x, y, and then dy dx. And then the x and y together make up my point, right? Remember, they're ordered pairs. And my dy dx is going to tell me the slope. And this slope is going to come straight from my equation. So in this case, it's equal to y. Okay? So basically, this is telling me that the slope at any point is going to be equal to my y coordinate. So one place to start that I like oftentimes is if there's an obvious like pattern or an obvious 0 slope. That's nice. So basically, if y equals 0, okay, if y equals 0, my slope is going to be 0 because it's literally my y. And my x can be anything. So let's just pick some values for the sake of our table. -3, 0, 1. So what that means is at the point -3, 0, the slope of the little line that I'm going to draw is 0, which means it is horizontal. So at -3, 0, like right here, I'm going to draw a horizontal line. Same with 0, 0, same with 1, 0. And this is going to be kind of hard to see for right now for the 0 because it's on the x-axis, but I can fill this pattern in here, 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 here. So basically I'm drawing a bunch of little things like this. Okay, like that, just horizontally right here. So the next thing is, let's say we try 1. So whenever y equals 1, my slope is going to be 1. So whenever y is 1, so x can be any number. So let's say -5, 1, 2, 1. The slope is going to be 1. So that means it's going to be upwards at maybe a 45 in this case, right? And at any point where y equals 1. Well, where y equals 1, the y coordinate is 1 anywhere along this horizontal line, right? So in all of these points here, when y equals 1, the slope is going to be 1. And I'm going to try and center that, center that on the points, which is why the dots are kind of nice. But okay, so just small lines like this, and like that, then like that, and these should all be parallel, and they should all have slope of 1, because the slope is the y coordinate according to our equation. And every point on this horizontal line has a y coordinate of 1. So of course, like I said, you don't have to do this at all all of the only integers. You can do this in between. This is just a visualization, but just to keep it clean and neat like this, you can. And I think it kind of conveys the pattern enough. So we'll just leave it as that. So then from there, I don't think we really need our table much anymore for this particular problem, but I hope that gets you started for making a table with other equations where it's not just y. But we will do that, like I said, in the future. And so for 2 at this point, whenever the y-coordinate is 2, which is anywhere along this horizontal line right here at 2, the slope is going to be 2. So for any point here, the slope is going to be 2, which is steeper than this one. It's going to be sharper up. And again, they're all going to be the same, so they're all going to be parallel, because lines with the same slope are parallel. Do, 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 do. We don't need to be super precise here, as long as we get the idea. Do and do. Okay. And the same deal with 3. And so I'm just going to start kind of estimating here, but when y equals 3, the slope is 3, so it should be sharper than this, but not quite 4, right? So somewhere in between, but it should not be parallel. It should still be steeper. So, I'm trying. Do, and they should be straight lines. Okay. And then 4, of course, is even steeper. I hope that's coming out. I hope you get the idea, right? So this should have slope 4, this should have slope 3. Maybe it shouldn't look quite so similar, maybe a little bit less. And then for negative, so it's 0 here, but then for negative, we should have, again, at y equals -1, the slope should be -1, which is downwards at that 45 at first. This is easier, this is the one that's easier to be more precise, but as we move forward, it's harder to estimate like a 4th versus a 3rd and whatnot, but it's okay. Okay. And then for -2, the slope should be -2. And again, I'm getting these values just straight from our equation. Okay. So it might not have like an obvious pattern like this where it's just all the way across. We still have to just try different values. But sometimes you can kind of find some, which will help. Some people suggested this because they thought it would look nice to do this by hand, and I hope that I'm doing this sort of justice. It's kind of hard. It's kind of tedious too, but it can look so beautiful. So, I don't know. Maybe I can print some out too that are digitized, but my goal for today is for it to make sense first, and then we can keep practicing the rest, okay? And then, of course, -4 be a little bit steeper than that. Doop, and doop. Okay, so this is our slope field for dy dx equals y. So I hope you're getting the hang of that. So then, of course, for -5 and 5, the slope will just keep getting bigger. Okay, and this is what we mean by slope field. So you just have a whole bunch of points, and at those points you have little line segments that have the slope of the value that you would get for dy dx when you plug in the x and y coordinates. So here we can fill in, let's just try half. Let's do one more y value of half. The slope would then be half. And I'm just going to make like a flatter one just at half. So I'm just kind of continuing the same thing. It should be half, so it's like that. But I wanted to, you know, you can get more precise with this as you do it, but doop, 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 doop. And I'm just throwing that one in because it kind of helps us see what's happening. So, like we already said, this is an example of one where you can solve for y in terms of x directly. Just remember to keep track of your domain and range and initial conditions if you have any. But this is one you can solve. But if it were one that you couldn't solve, from here we can actually get a general picture for a solution, just kind of sketching it, right? Not super accurate, but you can kind of get a sketch for what's happening without having an explicit formula. And you do that by kind of just following the flow. Following the flow. So for instance, this is not going to make sense. Like, this is not a function. You kind of follow the lines. The lines, remember, are derivatives at the points, and these lines are the tangent line. So of course we're talking very, very, very like super zoomed in at that exact point. So our lines are actually going to be teeny, teeny, teeny. But this is just a visualization of the actual tangent line. And remember, a tangent line touches our curve at exactly one point. So you kind of want to like trace out, this is sometimes called a direction field. And when you want to find the solution, you kind of let them guide you. Okay? So one solution from this might look something like, you know, this gets steeper. I want to kind of touch like that, like that. That's one. And sometimes I get a little shy to sketch this out because I take so much time to draw such a pretty slope field that I don't want to like mess up the sketch part, but and I might have already, but do you see what I mean? Like, as it gets steeper here, you expect the graph itself to kind of get steeper because these are tangent lines. They should touch at just that one point. You just kind of follow the flow. Okay, and same with this downward part. So something, maybe this one is better. Maybe like, this just means my drawing is really bad. Maybe like that. Okay. I don't know, maybe you can do a better job than I can, but you want to follow the, and if you need more points in between, you can kind of see what's happening. So if that helps too, filling it in. This might be kind of ugly, but I hope that makes sense. Like touching at just that one point there, but then touching at just one point here, and then just touching at one point there. There, that's better. It's all sketching anyways, but the reason that we have so many potential, so all of these little things that I'm doodling here are potential solutions, right? And why do I have so many? That's because that is going to be dependent on my plus C. So if a homework question, for instance, or a test question is estimate the solution at, you know, let's say 2, 1, you want the curve that goes through this point 2, 1. So that's this one. So I would estimate it to look something like this. Okay. So So you can get a general shape, kind of. To be more precise with this one, I would definitely pick some points in between as well. So like, you know, negative 1.5 has this slope, and you could have a clear idea of what you're tracing. Here I'm just missing a lot of in-between points, so it's kind of sketchier, haha. But you can actually extrapolate for this one because all of the y values are the same all the way across, so all the slopes are going to be the same, so it's okay if it doesn't, like, you know, you're not connecting the dots from this to this to this. You're just kind of following it as needed, so it smooths out. Okay, so I thought that this was interesting. I hope you found it interesting as well. If you see anything blatantly wrong, just let me know. But I got more and more sketchy as we went along. The slope of 1 is pretty accurate, but then from there, it's just kind of estimating. But of course, if you want to be very accurate, you have to do your change in y over change in x. And so usually, you know, when we graph lines, they're much longer, but since we're just doing all these little mini line segments, we're just trying to estimate anyway. Okay, thank you so much for joining me today, and I hope that you are doing very